Gigi is a rapid prototyping and development platform for real-time rendering developed by Seed. It's meant for use by professionals, researchers, students, and hobbyists. We've used it internally for collaboration between teams, we've used it in published research, and we've used it to generate code that we've shared publicly. Gigi is now open source, and this video is an introductory tutorial. By the end of this tutorial, you'll know how to create a box blur post-processing technique and how to apply it to a different Gigi technique. There are many features of Gigi that we won't be covering today, but this should be enough to get you started. The first step is to download Gigi from this GitHub repo, which is at github.com/electronicarts/Gigi. One way to use Gigi is to build it from source. To do that, you clone this repo and build gigi.sln in Visual Studio. Another way to use Gigi is to use the pre-built binaries. To get to those, you go to the releases section, and you can either grab the zip file, which is a zip of the binary package, or you can run this installer, which will install it. I've downloaded the zip file and extracted it so we can work off of that. After you've built or downloaded Gigi, there are 3 executables. GigiEdit.exe allows you to make and edit techniques. GigiViewer dx12.exe allows you to run, debug, and profile your technique. It also supports hot reloading of shader files, asset files, and Gigi files to allow rapid iteration. Lastly, GigiCompiler.exe is a command line utility which will generate code for your technique. So let's open up the viewer to take a look at a few techniques that come with Gigi. Gigi comes with a bunch of techniques built in the techniques folder. This includes the unit test folder, which has techniques to exercise every feature, and those techniques work as minimal examples of how to do almost anything you might want to do. In the shader toy folder are some shaders I've made in years past that I ported to Gigi. We can start with the Minesweeper game, which lets you left-click to reveal a square and right-click to place a flag. If you die, you can click the reset button to reset the map. Every time you play, it has a new map because it uses the current time as a random seed. This was all made in Gigi, just nodes in a shader graph in HLSL, no C++ or scripting languages. Next, we have a stylized path tracer. You can see a rough reflection on the floor as we fly around. The cactuses and the triangles were ray marched, not ray traced, and there's a slight amount of depth of field in the background. There's also a 2D Verlet physics-based car game. This is all running on the GPU, again, using compute shaders. You use the arrow keys to drive your car forward and do tricks. And the goal is to collect the red balls to get more fuel and make it as far as you can without crashing. If you do crash, you can just hit spacebar to reset. Lastly, let's look at some real-time machine learning on the GPU. Some of you have seen my video or blog post on machine learning for game developers that walked you through how to train a neural network to recognize handwritten digits. That material included a DX12 demo that allowed you to draw a digit and have it do inference in real time, telling you which digit it thought you drew. Believe it or not, that demo was made in Gigi, and here it is running in real time. We generated the code for DX12 and shipped that out, and that's what we put in the repos. But you can't tell by just looking at the code that Gigi had made it. It looks like a human wrote it. So here the demo's running, and I can draw a 1, and it thinks I drew a 1. A 2, it thinks I drew a 2. I can draw a 4, and so on. While we're in the viewer, you can also click on the Profiler tab, and it tells you how long each step of the graph is taking on both the CPU and the GPU. So let's close the viewer and start making our own technique. Let's save our technique in the techniques folder and call it box blur. So the main concept in Gigi is nodes. There are resource nodes, which are textures or buffers, and there are action nodes, which can do things like run a compute shader, run a raygen shader, copy resources, or do a draw call. The nodes are strung together into a graph by piping resources through action nodes for either read or write access. The read and write access is what defines the constraints of the ordering of the work when it's flattened to be submitted to the command list. In this technique, we're going to make a blur that takes an input texture, blurs it, and gives the result as an output texture. So first, let's make our textures. We can right-click and choose Resource Texture, and we can name this Input. Every resource has a visibility that's either imported, internal, or exported. Imported textures come from outside the technique. Internal textures are created by the technique and cannot be read or written to from outside of it. Exported textures are also created by the technique, but are meant to be readable and writable from outside of the technique. For our input texture, we want it to be imported. Textures also have a format and size that you can set, but for our input texture, we want it to accept any format and any size, so we'll leave those alone. To make our output texture, we can right-click again, choose Resource Texture, and we can name this Output. We want this texture to have a visibility of exported since it's the result of our work, so we make sure and set it to exported. For format and size, we want it to be the same as the input, so we'll choose Input under the node dropdown for both format and size. If we didn't want that, we'd be able to specify a specific format or size, either in this format dropdown or by using these multiply, divide, pre-add, and post-add fields of the size. These allow you to have either relative sizes, so you could have a double size texture, or you can also do absolute sizes as well using these. So let's save. In the editor, you can use the mouse wheel to zoom in and out. You can use right mouse drag to move around in the window, and you can press F to bring the whole graph into view. Next, we need a compute shader to act on them. We can right-click and choose Action Compute Shader. And we can call this Do Blur CS. Do Blur CS. This compute shader doesn't yet have a shader to actually run, so down here in the Shaders tab, we can click New to create a new one, and we can call this Box Blur CS. We'll leave the file name blank for now. For the type, it's set to compute by default, which is correct. But there are other type of shader types in the dropdown, like vertex, pixel, and raygen. For entry point, we can call it CS main. And there's a defined section where we could add defines if we wanted to, but we don't need any today. Num threads of 881 looks good to me, but we'll need to define what resources the shader wants to read and write. So here under the Resources tab, we will create a new resource and we will call it Input. We'll make it of type texture, and the access will be SRV, which means read. And here under the Texture tab, we could set the dimension and the view type, but a 2D texture that's viewed as float 4 is what we want. So that was it for our input texture, but we need to make another one for our output. So we'll add it and call it Output. This one is also of type texture, but its access is going to be UAV, which is read and write. And once again, texture 2D viewed as float 4 is correct. So we can save, and then now coming back to our compute shader node, under the shader dropdown, we can choose Box Blur CS. And when we do that, the resources we define show up here as pins, letting us know if it's read or read write. And we can plug in our pins just like this. The next thing we need to do is author our shader file. Under the Shaders tab, you can scroll all the way to the bottom and click Create Shader File. We'll call ours boxblurcs.hlsl. At this point, Gigi has created a skeleton shader file for us. If we double-click the Compute Shader node, it will open up the shader in your default shader editor, which is VS Code for me. The top line is a comment, but below that is this shader resources token. When Gigi techniques are compiled, the shaders undergo string replacement before they get to the shader compiler. These tokens are places that the Gigi compiler looks to do string replacement. This particular token is where Gigi will put the declaration of any textures and buffers that the shader reads or writes. Gigi inserts these instead of getting them through shader reflection because different platforms want shader resources declared in different ways. When Gigi inserts the resource declarations, that allows shaders to be generated to work on more platforms. The next token is the Compute Shader Entry Point token and defines a computer shader entry point named CSMain. At the bottom is a helpful comment that says what resources are available to the shader and what type of access they have. Okay, so let's write our blur. We're going to start off with a color. This is going to be what we are writing to the output pixel, and we're going to do a double for loop. And it's very important that we include both -1 and +1, and so that's why it's a less than or equal to. So that's Y on the outside, we're going to do X on the inside. Next, we need the pixel location of our input and output pixels, so let's get that. And let's read our texture. And only the RGB channels. We don't care about alpha right now. And in a box blur, you're averaging all of your samples, so we need a weight to keep track of how many samples we have. And then now, after the for loop, we can divide by the weight to make sure it's normalized and we're getting an average. And then we can write the output with an alpha of 1. The reason we're doing a weight instead of a divide by 9 is because later on we'll be making the blur size variable. Keeping track of a weight in a blur is useful for when you're doing something like a Gaussian blur or a depth-aware blur. In these cases, the weight of each contribution may not be 1, and you might not even take every sample within your kernel size. So keeping track of a weight is a nice way to make sure your blur is normalized. So now we save the shader, go back to the editor, make sure that's saved, and then we can click on Open Viewer to see it in action. Here we are in the viewer and we don't see anything. If we expand our compute node, it says that it can't run because the input texture doesn't exist. We told the editor that our input texture was imported, and we haven't specified any texture for the input, so that makes sense that the input texture doesn't exist yet. In the Imported Resource tab, we can see the input texture listed right over here. We could set a fixed size and color image for our imported texture here, the input, but blurring a constant color image doesn't make a lot of sense. What we actually want to do is give it a file. So we can click this button here and go into the Techniques folder and choose Cabin Small. Now we can click here on our output, and here's our results, but it isn't quite what we would expect. There's some color in the upper left, but that's it. This is because we haven't yet told the compute shader node what the dispatch size is. If we go back to the editor, we can do that. So we click on the compute shader node, and under dispatch size, we tell it to dispatch whatever the size of the input texture is. So when it's actually calculating the dispatch size, it will divide the size of the input texture by the num threads and round up like you'd expect to get the actual dispatch size. So let's save that, and then let's go back to the viewer. And there we are, the results of our blur. Let's look at this a little bit more though. In the upper right is the render graph window. By default, it only shows resource writes and it hides resource nodes. We can uncheck those to see more of the render graph. And we can expand those out. And so this first section shows the input texture at the beginning of the frame. This shows the output texture at the beginning of the frame. And then here it shows the input texture as it's going into the do blur CS node. Here's the output texture before the compute shader has run. And here it is after. As you can see, it's hard to tell whether or not it's blurred because the image is darkened so much, right? If we flip back and forth. The reason for that is because we're mixing up the sRGB and linear color spaces. We're using an sRGB format for the texture, which we loaded, and that's correct. And our output texture is also an sRGB format, which is also correct. In the compute shader, when we read the input texture, it is converting from sRGB to linear like we want, and that happens automatically. So we are blurring in linear space, which is also correct. The problem comes up in the UAV write. UAV writes don't convert from linear to sRGB, which arguably that's a quirk of DX12. So let's go open the shader file and we can fix that. This isn't the best linear to sRGB conversion, but it works okay. And what we do is we take the color to the power of 1 divided by 2.2. And we can save that and then go back to the viewer. And we can see that it's hot reloaded our shader and that the colors are no longer darkened. We can flip back and forth. We did make a mistake when writing the shader though, so let's go back to the shader. In the for loop, we read the same pixel 9 times instead of offsetting it by the for loop values. So let's add the offset in, and then we can go check it out in the viewer. So here's the offset. We can save that, and then go back to the viewer. It might be hard to see in the video, but if you click back and forth between the input and the output, you can see that we've definitely blurred the image. Some other functionality of the viewer worth mentioning is that you can mouse wheel to zoom in and out. And if you zoom way in, you can turn on and off the linear filtering if you want to see the actual pixels or not. And that's just turning on and off the bilinear filtering. You can adjust the histogram like you could in something like RenderDoc. Put like 0.5 here. And then you can also either reset the histogram or click auto to do an auto histogram. You can also turn off color channels if you want to look at just specific things, like if you only want to see the red channel or the green channel, you can do that. It also tells you the size and the format of the texture up here, and you can click on individual pixels and it will tell you what their value is. Next up, let's add a parameter to our technique that controls the size of the blur. We do that in the editor. To do this, we're going to use a variable. Variables are a concept in Gigi that help glue things together in ways that you would normally need custom CPU-side logic for. Variables can control resource sizes, they can control dispatch sizes, they can control which nodes are executed, and they can be read by shaders. When doing code generation, depending on the target, variables can also show up in UI, scripting interfaces, and can be read or written to by the host application. We're going to use a variable to control the blur radius. So in the Variables tab, which is right here, we can click New, and we can call this variable blur radius. So we need to set a type, and so we can set it to int, and give it a default value of 1, and we also want its visibility to be user. So variables have visibility like resources do, which control what they're visible to and what can read and write them. Internal means a variable can only be read to or written by the technique. Host means that the host code can also read and write the variables. User means that the variable should also show up in the scripting interface or the UI or the console variables or similar, depending on what's available on the target platform. So let's save this, and we can go back to the shader file. So how we read variables from shaders is by using tokens. So let's do that. Static const int c blur radius, and we'll set it equal to variable blur radius, just like that. And then now wherever we have -1 or +1 here in the loops, we can just put in our blur radius instead, and we can save that. Now we go back to the viewer, which is hot reloaded it, and we have this blur radius right here showing up in the Variables tab. And now we can just adjust this number and adjust the blur. If we set it to 0, it even turns off the blur. But let's set it to 20 for now. If you're wondering how the variable gets to the shader, you can see how from the viewer. In the Shaders tab over here, you'll see two groups of shaders listed. There's the shaders and the process shaders. The shaders are the shaders we've been editing, and the process shaders are the shaders sent to the shader compiler after Gigi does string replacement. So click on Box Blur CS in the process shaders section to pop it open. We can see in the shader code that the shader has our input and output textures, and it also has a constant buffer. The struct the constant buffer uses is above it too, right here. And it shows blur radius as a member. Going down to our static const int where we were reading the variable before, we can see that it's replaced the variable read with a read from the constant buffer. So how this works is that when Gigi processes shaders for string replacement, it also scans for any use of variables, and if it finds any, it'll make a constant buffer and get them to the shader for use. A similar fun feature Gigi has is that you can declare that you want to read a texture in a shader with a Gigi token, and you give it a file name and a texture format and some other parameters. And Gigi will load that texture for you and send it into the shader. And this is real handy for noise textures or VFX textures. And I'm not going to be showing that to you in this tutorial, but there's plenty of examples in the techniques folder. But while we're looking at process shaders, I should mention that Gigi supports making variables const. So we can go back to the editor. We can just set blur radius as const right here and then save it. And so const variables can't be changed at runtime of the technique. They have the value they have, whatever was set in the editor, and they can't change. So if we go back to the process shader, we can see that the constant buffer is gone, and our variable read from the constant buffer has been replaced by a literal. And so this is pretty handy because it allows the shader compiler to be smarter about optimizations, and it might decide to unroll these loops or similar if it decides to and make the shader smaller. A place that you might want to do this is like if you want a parameter that you can change from the editor, but at runtime, you want it to always be the same thing. This allows you that flexibility. Let's go to the viewer. And when you're in the viewer, next to blur radius, you'll see this thing that says const, and that lets you know it can't be modified in the viewer. It has to be changed in the editor. So yeah, we can go back to the editor, take off const, save, and then back in the viewer, or the process shader, there's the constant buffer struct read again. And then in the viewer, you can once again adjust the blur radius, and we'll put it back to 20. And note that in the viewer, you can see more than just textures. You can also see buffers. And so, for instance, here's the constant buffer, and we can see that our blur radius is 20 right there. And as we change this value right here in the variables tab, it also changes there. People have commented that it is very easy to debug things in Gigi in a way that is usually a lot more difficult. I'll show you what I mean. We can add a texture resource to our shader called debug. We'll make it of type texture, and the access will be UAV. Next, we can make a texture node. We'll call it UV. And the format, we'll make it the same size as the input again, and the size, we'll make it the same size as the input. And then we can plug it in like that and save. Next, we can go to our shader before it's processed, and we can, let's write the UV out to that texture. So first we have to get the dimensions. And then next we can write our shader, our debug texture out. Float 4, we'll write the UV in red and green, and then 0 and 1. Save that, and let's go to the viewer. So yeah, we can scroll down and we can see our new UAV attachment here showing us the UV. So in less than a minute, we were able to make a new texture that let us visualize some value that we calculated in the shader, which can be real helpful for debugging. So we have a modular blur technique. Now let's see how to use it. And we can do that by opening up the Verlet Physics Car shader toy. So let's do that. Zoom out a bit. So how we use graphs and other graphs is by using the subgraph action node. And we can make one and call it blur. For the file name, we're going to choose the technique we made, which is called box blur, which is right here. When we do that, the resources appear as pins on the node. We add an imported input resource, and we add an exported output resource. And you can see from the pins that it wants us to give it an input resource, and it will give us an output resource. So to hook it up, we can just take the output of the display and plug it into the input of the blur and save. So let's pop open the viewer. So right now we're looking at the output of the rendering like we were before, but we can just open this up and click right here and open this up, and we can totally adjust the blur amount. And then from here, we can play it. And as you can see, it just works without any hassle, which is pretty cool. And as you might notice here in the render graph, we even have our debug texture still, which you'd probably want to remove if this blur was meant for other people to use. The last thing I want to mention is that the viewer is able to run Python. We use it to run unit tests in the viewer to make sure the viewer is functioning correctly, but we've also used it in some of our research papers to gather data for RMSE graphs for numerical convergence, and also to generate images for diagrams. In the user documents folder, there's a viewer document that explains the viewer Python interface. To show you how it works, I'll run the unit tests. You just go File, Run Python Script, and you go to techniques/unit-tests/runtests.py. As it's running, the unit tests are opening Gigi files, setting settings, rendering, and doing readback. They do this to make sure that the resources they read back from the GPU match the gold images on disk. And it's already finished. And you can see that all of the tests have passed. It reports it in the log here at the bottom. The Python interface has been super useful for automation, and in fact, Gigi is deterministic by default. You have to go out of your way to add non-determinism by setting in clock time or writing shaders in a way that execution order is meaningful but not defined. Before I go, I want to mention that while Gigi is absolutely used software within EA and Seed, it's also very young. As you use it, you might hit bugs or missing features. Please report these issues in the GitHub repo as you hit them. Even if it's something we already know about, hearing from people using Gigi helps us understand how to best spend our development time. Thanks for watching, and I'm looking forward to seeing what you create.